Hi, everybody. This is Professor Monty. We are jumping into Chapter 4 today. Now, Chapter 4 is a little interesting because we've been doing a lot with derivatives. Now we're going backwards from derivatives. So we will have the rate of change of the function. We need to find the original function that came from. So let's just jot down that we are, in fact, going backwards from derivatives. So we are finding antiderivatives. Let's clear that up a little bit. And then the process of finding antiderivatives is called antidifferentiation. But for instance, say we want to find a function whose derivative is 3. Now, if we look at something like that, think about this. If we do f of x equals 3x, that works. But if we do, say, g of x is 3x plus 7, well, that also works, right? Since the derivative with respect to x of 3x plus 7 is just 3. Check. So we know that also works. But what about if I said h of x is 3x minus 2? That works as well. So we take the derivative. That, of course, we just get 3. So in general, what we're going to write the antiderivative of 3x, of 3 is 3x plus c, where c is any constant. And so when I just wrote 3x, that fits that because the constant in that case would just be 0, which of course 3x plus 0 is the same as 3, plus 7 minus 2, they all work. And the way we write this, here's our notation. We write a little symbol like that. It comes from the old-fashioned S. It's called the integral sign. And we'd say the integral of 3 and dx with respect to x, just like we did with the derivative d dx, is equal to 3x plus c. So that would be the way we write it. And we call this the integral sign. And so in general, that's the idea of what we're going to do. So now there's some rules, there's some shortcuts, just like we saw with derivatives. And so let's list some of these. The first one is, if I have the integral or the antiderivative of some constant, and I know that's a constant because I'm going to put dx. So x is the variable. So k can't be a variable, it must be a constant. Well, that just took place with the 3 we had before. That would just be kx plus c. We always have to put in the plus c because we don't know what the constant might be. So there's our first one. It just says the antiderivative or the integral of a constant is the constant times x. The other one is our power rule. Now, if I've got x to the n power, again, with respect to x. Now notice that integral sign and the dx go together. You can't have one without the other. It wouldn't make any sense. Well, remember, we would take that n down in front and then drop it by 1 if I'm taking the derivative. Well, instead of dropping it by 1, I'm going to add 1 to the exponent. Let's clean that up a little bit so that it's clearly a plus. So it's n plus 1. But then in front of that, we're just going to have that n plus 1 just flipped over. So we're going to have that again plus c. And we'll do examples so that you see these all actually do work. But just put the reciprocal right in front of the x, the reciprocal of the new exponent. So I always go to the exponent first and then take its reciprocal. The third one, remember, we saw something whose derivative was 1 over x. And if you remember what that was the ln function. And it's actually ln of the absolute value of x, because we can have negatives there. We're going to show what this means geometrically in another section. So at this point, we're just taking the absolute value of x again plus c. And then the fourth one we see is if I've got the integral of e to the a times x. And we've seen this before. If I take the derivative, it's e to the ax, but then times a from the chain rule. Well, instead of times a, we're just going to divide by a. So it's just going to be 1 over a, and then e to the ax. Again, as always, plus c. So those are the 4 shortcut rules that we see. There's another 2 properties I'm just going to put with these shortcuts so that we keep everything together. Well, that didn't come out the way I'd hoped. And one is just if I'm integrating a constant times a function, with respect to x, I can just pull out the constant. Just like it's the same constant multiple rule that we use with derivatives. We can just take it out and just multiply the constant after we take the integral. And then the last one is just saying if we're taking the antiderivative or the integral of a sum or a difference, just like the derivatives, we can just break that up into 2 separate integrals. Take the integral f of x dx, and then plus or minus, and then the integral of g of x dx. So there's our properties and rules. So we've got 6 of them we have to pay attention to, and then that's the entire lesson. The rest, I'm just going to show you some examples. We'll do a couple of things where we'll find the c actually when we integrate, but they have to give us some more information. So we'll do that shortly. So let's just do some examples of each of these. So for example, and we've already seen this one, if I've got the integral of 8 with respect to x, well, that's my constant, so the antiderivative is just 8x plus c. And notice you can always check these by taking the derivative. So if I say, well, what's the derivative of 8x plus c? Well, I know I just get the 8 from the 8x, and then the plus c just goes to 0. So it's just 8. Oh yeah, that's what I started with. So I know it's right. Oftentimes we just check in our head, but I do suggest you do a real quick check there to make sure you are doing it correctly. And then suppose I have something like x to the 4th power with respect to x. So this is what I was saying before. I'm going to add 1 to the exponent and then multiply by whatever the reciprocal of that new exponent is. So, and I don't put the plus 1 when I'm writing it down. I'm just in my head. I know it's x to the 4th. I know I'm adding 1, so I'm going to say, oh, it's x to the 5th. Oh, so it's 1/5 x to the 5th plus c. And there's my answer. Again, let's check this one real quick. I'm not often going to show the check, but if I take the derivative of what I have as my answer, I should, in fact, get back to what the original problem, what I was taking the antiderivative of. And remember, we're just going to bring that 5. That 1/5 is a constant multiple. It stays. I bring the 5 down, and then I go x to the 4th plus 0. And, of course, that's why I had the 1/5. It's going to cancel that 5. I just get x to the 4th. So, again, it does check real quickly, real easily. Okay. So let's jump up and look at some problems that are a little more complicated than that is. So let's see, let's do this. Problem 8 out of the book, it's the antiderivative of x squared minus x plus 2. So on this one, what I'm going to do is I'm going to use that one property that says, hey, if I'm adding or subtracting, I can do these individually. Now what I'm doing, and I usually don't write this down, but in my head, I'm thinking, oh, it's the integral of x squared minus the integral of x plus it's the integral of 2. And then I just do each of those individually. Again, I usually don't write that down, but for our purposes, I will write that down so that we see exactly what I'm doing. And when I do the first one, remember, I'm going to add 1 to the exponent and multiply by whatever the reciprocal was. This one's x to the first power. So again, I add 1 to the exponent and multiply by the reciprocal. And with the 2, that's what I saw before the constant. I just put the x there. So I added an x just like I did on the other ones, and then plus c. And technically, you may be thinking, wait, don't I have 3 plus c's in there? Yes, you do. But if you add 3 constants together, you're going to get a constant. So we usually don't put the separate c's in there. We don't know what their value is anyway. We just know altogether it's adding some constant. And so we just put a plus c at the end. So I get 1/3 x to the third. Again, you could probably do that in your head in one step. Minus 1/2 x squared plus 2x. I don't like that 2x. Plus 2x plus c. And this one, I'm just going to take the derivative in my head. The 3 comes down, cancels out the 1/3. I get x squared. Yeah, I have x squared up there. Minus the 2 and the 1/2 cancels. I get x to the first, yes, plus 2, and then plus 0. So I can check real quickly to make sure I have the right answer. All right, so let's make them a little more difficult than that. It's fewer steps. It's problem 12. It's just the integral of 1 over x to the 5th. And just like derivatives, the key there is remembering, oh, that really means x to the -5 power. But then to do it, I do just what I've been doing. I add 1 to the exponent, and I multiply by the reciprocal, plus c. So I'm going to get, notice that's x to the -4, and so it's 1 over -4 plus c. And you can leave it that way, or that x to the -4, that's going to go down to the denominator. So it's really, we'll put the negative up front. It's 1 over 4x to the 4th plus c. And so both of those are the correct answer. It just depends on the form you want. We used to say in algebra, you can't have negative exponents in the answer. Well, we let you do it in calculus. So it's not as much of a rule in calculus. It's more of an algebra rule. All right, let's look at problem 16. So as you can see, these go fairly quickly. This time we've got the integral of the 3rd root of x squared. And again, that's why we learned all these ways of writing exponents in algebra, because I'm going to write this as the integral of x to the 2/3 power. Remember, the root is the denominator of the exponent. And now I do the same thing. To do that, I'm going to add 1 to the exponent and then multiply by the reciprocal. Now, I really don't do this part where I multiply by the reciprocal this way, because here's what I'm thinking. Don't forget your plus c. Here's what I'm thinking. 2/3 plus 1, notice that plus 1 is really 3/3. So I get x to the 5/3. Well, the easy way to do that, remember I've been saying multiply by the reciprocal. Oh, that's just 3/5. And then again, you're done. You can add those on the bottom. 2/3 plus 3/3 is going to be 5/3. Oh, invert multiply, now it's 3/5. But the easy way is just figure out what the exponent is and then multiply by the reciprocal. All right, so zip it along. Look at problem 20. Now they write it this way, 2 over x dx. And what a lot of us think, we think, oh, that's easy. That's 2x to the -1 dx, right? And I add 1 to the exponent, and I multiply by the reciprocal, plus c, and I get 1 over 0, x to the 0 plus c. But of course, when I see this 1 over 0, that's undefined. I can't do that. I can't use the power rule if I just have x to the first on the bottom. X to any other power is okay, but x to the first on the bottom, I can't do it that way. So what I do, I have to think, well, how can I do this? Let's erase all that. That's actually that other property I showed you. Remember, we're going to use 2 properties here. One, let's pull out the 2. It's a constant multiple. And then think, what has the derivative of 1 over x? The ln function. So it's really 2 ln of absolute value of x plus c, done. And again, you can take the derivative of that. Let's do that real quickly on this one, because I have 2 times the ln, that doesn't look like it times the ln of x plus c. Well, the 2 is a constant multiple, it stays there. The derivative of ln of x is 1 over x, and then plus 0, so I just get 2 over x. It's a weird looking x, isn't it? Check. So those you kind of have to be on the watch for, is because we don't see those as much. We are usually using that power rule. All right, let's look at problem 26, if that'll move up for me. It's the integral of e to the 5x dx. Again, remember, if we're taking the derivative, we're going to get e to the 5x, but then times 5 from the chain rule if we're taking the derivative. We're not taking the derivative, we're going backwards, we're doing the antiderivative. So instead of multiplying by 5, you're going to divide by 5. Plus c, and actually we're done. That one, again, think about if you take the derivative, it's going to be e to the 5x times 5. That times 5 is going to cancel the 1/5. Okay, so that's the idea that, they'll throw in some other things that you have to do, but that's all the properties we saw. So we've used them all. Let me show you how to do these with initial conditions so that we can get the actual function itself. We're going to deal with that plus c. So here's an example of that. This is problem 48 out of the book. Obviously, we're jumping up a little bit. They tell us f prime of x is x minus 5. They also tell us f of 1 equals 6. And the question says, find f. So they want us to find the original function. Well, the key here is that the original function f of x is the antiderivative of the derivative. So that antiderivative is going to get rid of the derivative. I'll go back to the original function. So in this case, it's the antiderivative of x minus 5 with respect to x. So what do? I add 1 to the exponent. It's x to the first, now it's x to the second, multiplied by the reciprocal. Minus a constant gets an x, and then plus c. But I'm not done. I know what my function looks like, except I've got that plus c, but they told us up here, f of 1 is equal to 6, meaning when x is 1, the y value, or the function value, is 6. So now what I do, I plug those in. So if that's my whole function value, I say, oh, when x is 1, then the function value is 6. And you can put the 6 on the right side or the left side, it doesn't matter, just have an equal sign in there. And now what I'm trying to do is solve for c. So I say, okay, let's see, 1 squared is 1, so I get a half. Minus 5 plus c is equal to 6. Not a big fan of fractions. Most students don't like to work with those. So what I'm going to do is I'm going to multiply both sides of the equation by 2 to get rid of my fraction. And on the left side, I've just distributed. I've used the distributive property to multiply each piece by 2. Those 2's cancel. So I get 1 minus 10 plus 2c equals 12. The 1 minus 10, of course, is negative 9 plus 2c equals 12. Now I can add the 9 to both sides. I'm going to get 2c is 21, and then divide by 2, c equals 21 halves. That's my constant. So my function, I already knew up here what it looked like. So I'm going to say, oh, my entire function f of x is 1/2 x squared minus 5x, but I know c now, plus 21 halves. And there's my function. And if I want to check it, I do 2 things. I take the derivative, make sure the derivative is x minus 5. It is. And if I plug in 1, I should get 6 as my answer. And I'll leave that for you to check. But hopefully you will. Okay, so anyway, that's an initial condition problem. Let's do another problem like that, and then we'll do an application with that as well. So let's try another one of these. This is 54. F prime of x, 3e to the 4x. f of 0 is equal to 7/4. So again, I'm taking the antiderivative of the derivative, and this is going to be the original function. And so I do this, I get, remember 3 is a constant multiple, it stays out, but then that e to the 4x I get, but instead of times 4 from the chain rule, I have to do multiplied by a fourth, again, plus c, that's my function. So again, let's plug that in for x and that in for y. So I get, let's call it 3/4 e to the 4x plus c equals, now it's equal to that 7/4, and I wrote 4x. Let's change that x here to a 0. So it's 4 times 0. Now that, of course, is e to the 0, and e to the 0 is 1. So this ends up on this side just being 3/4 times 1 plus c equals 7/4. And of course, 3/4 times 1 is just 3/4. So now I'm going to subtract the 3/4 from each side. And then 7/4 minus 3/4, 4/4. So I get c equals 4/4, which of course is just 1. And so my function, let's go back up here, it's essentially here. Is that going to fit? F of x is 3/4 e to the 4x, and then plus 1 from down here. There's my function. And again, you can check by taking the derivative, making sure it's 3e to the 4x, and making sure that if you plug 0 in for x, you get 7/4, which you will. Clearly, it's 3/4 plus 1. All right, let's do an application here. Let's see if I can paste it in, or if I have to go grab it. How about that? So we've got demand from marginal demand. So they give us the marginal demand function, or the derivative of demand. Lessard and Company finds the rate at which quantity of flameless candles that consumers demand changes with respect to price is given by the marginal demand function. They give us the function where x is the price per candle in dollars. Find the demand function if 1,003 candles are demanded by consumers when the price is $4 per candle. Okay, now notice a couple things. Right here, 103 candles are demanded when the price is $4. So that means, so x, that's demand. I said that wrong, didn't I? X is price, and d of x is demand, or quantity. So this down here, what they're saying is when x is 4, demand is 1,003. So it's a what they call an initial condition problem like we had before. This up here, I'm going to rewrite as negative 4,000 x to the negative 2. And so now when I want to find my demand function, again, that's the antiderivative of the derivative of demand, which in this case is the antiderivative of negative 4,000 x to the negative 2 dx. Remember, I can pull the negative 4,000 out. That x to the negative 2, I add 1 to that. It's going to be, here we'll write it, negative 2 plus 1 is going to be negative 1. Multiplied by the reciprocal, plus c. This is my demand function. Should I write d of x right here? And so I get my demand function d of x is, now I've got this negative 4,000. On the bottom, I've got a negative 1 is what that's going to be. So the negative 4,000 divided by negative 1 is positive 4,000. X to the negative 1 plus c. And let's make sure that's right, because if I take the derivative, I get negative 4,000 x to the negative 2. Yeah, that's what I had as my derivative. So I'm in good shape. Now the demand, well, the demand was 1,003 when x was 4. Now, if you remember, that negative 1 is going to put it down to the denominator as a fraction. I don't know how that turned into 1,000. So I get 1,003 is equal to, that's really 4,000 over 4. 4 to the first, right? So that's just 1,000. So I get 1,003 equals 1,000 plus C, or obviously when I subtract 1,000, I get C equals 3. Well, that's what I'm going to put in here. And so my demand function, I'll just put it here so I have room and I can see everything. It's, well, here's my demand function. I'll use that. 4,000 x to the negative 1 plus 3. And we can write it that way. Often they will work with that negative exponent and they'll write the demand function as 4,000 over x plus 3. I like that way better. They are obviously the same type of thing. They're equivalent functions. And then now if they ask you a question saying, hey, what's going to be the demand? And let's even make this up. Find demand when price equals $10 per candle. All right, so that just means x equals 10. We just plug it in. Oh, the demand at $10? Oh, that's 4,000 over 10 plus 3. Let's see, 400 plus 3? 403 candles. So once we've found the original function, then it's much easier to get any demand for any price that we have. All right, but anyway, that's the end of that section. Hopefully that helped out. If you have any questions, obviously ask me in a live session or post a question in the chat or just send me an email. All right, you guys all have a great one, I hope, and I will talk to you again shortly.